is 0. You need to get access to SM Ram. Because System Mode Ram or SM Ram exists, and like System Management Mode is basically a 16-bit operating mode, it's expecting not to have like. I'll just go through each step and then explain it step by step. I'm getting ahead of myself. So the first part is you need a mechanism for ensuring that SM lock is 0. If it's 0, all related MSR, like all SMM related MSRs may be written to when you're in ring 0. That means you could reconfigure the handler on the fly, which creates some really weird configurations when you experiment around with it. And they actually provided you a mechanism, which is another model-specific register called SM Key. And what SM Key does is, if the system management mode lock is set, but before you set it, you happen to do a write to SM Key, it basically becomes a password that allows privileged code to unlock SM lock. The thing about SM lock is that if SM Key is not set, and it's set to 1, the only way to unset SM lock is to actually reset the machine. So again, when I said earlier that you could have a BIOS, you could have somebody who subverted the BIOS, they can subvert it up to a point. Provided that they actually leave, like if you're expecting an SM key value to be set before the SM lock is set, then you can always unlock the bit. If they don't do that, and if they don't actually set SM key for you the same way you expect it, what will happen is that when you go to check for it, like as you can see in the sort of pseudocode I have up here on the right, essentially you know that you have an uncooperative BIOS. You're going to assume that like if you're going to build a system like this anyway, your BIOS has to cooperate with you to get around this. So you know you're sort of boned at that point. So it's like, all right, I mean, in my case, I was just halting the machine if I couldn't find that. I also discovered while developing that I was using the AMD SimNow simulator. I discovered that in some configurations, including the one I did most of my development on, it didn't actually support the SMM Key MSR. And if anybody's seen me ranting on Twitter about like random outputs where I was offering $100 to anybody who could explain what it was, it turns out that what it was me writing into the MSR and just having the simulator go, I have no idea what to do with this. So followed by crashing. You know. All right, so now that we've made sure that we can actually turn the bit off, right? So we've turned the SM lock bit off. We need to get access to SM Ram. The problem is SM Ram is supposedly only accessible from SMM. Again, like I mentioned earlier, there's a system management mode control like MSR. What this does is it lets, like, by writing certain patterns into the MSR, we can like simulate different portions of system management mode. So we can say, okay, SMI enter. What that does is it actually says, okay, I'm going to map SM Ram, put it up there, and then you can start copying from it directly from your privileged code in the virtual machine monitor, or you could even just set up like page tables and everything else in place using SM base as the start of your virtual machine, and you figure out the size of SM Ram, at which point you don't have access to it. The other thing too is that by doing this, you also prevent other like SMIs from being asserted at the same time. So all right, so like I said, like you have to run this in a virtual machine. In order to run a virtual machine, you basically have to allocate and configure a virtual machine control block for what I'm calling the System Management Mode Virtual Machine, or SMM VM. One of these days we'll come up with better terminology because I'm just going to stumble over it if I keep saying it all the time. But in order for this to work, the specific requirements are you need to be in paged real mode. Paged real mode is an operating mode in which your virtual machine protections, all of your virtual machine monitor protections for memory are based around the concept of paging. Real mode code and 16-bit mode code assumes that there are no page tables and assumes it just has raw access to memory. It's based on the segmentation model where you have like a segment and an offset, and that's your address, and it figures everything out from there. So in order to apply memory protections to this kind of code, you need page tables. So they added the paged real mode, which actually lets you set the paging to 1 and protected mode to 0, which is actually an illegal processor state unless you're in a guest. You need to be able to set CR3 to the physical address of like guest page of the guest page table, which is really a shadow page table, which since SMM doesn't actually use a page table, it doesn't use paging. This is just your shadow page table to translate addresses. Then you need to set like the virtual machine control block to intercept page faults, because you're going to run into that where you have to update page state and anything else because memory will be accessed. And finally, because you have to control the return from the system mode interrupt handler, you have to intercept the RSM instruction. The other thing that's important to do is also do, like, if you have a malicious handler, it may try simply to disable the system for some reason. Let's say you have like an availability scenario or whatever. There are a bunch of states that are like very illegal to run an SMM, like when you're running an SMM that you can't do. Some of them, unfortunately, are not coming to mind right now. But basically, you need to intercept like shutdown, because if any of these conditions are met and it causes a shutdown and you're running as a virtualized guest, but you don't actually catch shutdown, then the processor is just going to shut down. You lose the whole machine, or it turns itself off, really. And the last thing is that since we're opening up SMM lock, we need to make sure that we control, the virtual machine monitor actually controls access to the system management mode MSRs. So we need to intercept all of the writes to those SMM MSRs. And basically, we sort of virtualize them where we just say it doesn't happen. Say, all right, you tried to write to it, intercept it, get rid of it. Okay, and so now we have our guests. What do we need to do for our guests? We need to prevent writes to MSRs by configuring the model-specific register permission map. We need to make sure that we intercept writes to the hardware control register, because if somebody has the ability to reset SM lock back to 1, all of our intercepts go away. At which point now we're in a lot of trouble because we've lost the ability to virtualize or to containerize this. The other thing too is that since we've set SM lock to 0, we need to make sure that any of our guests don't attempt to move where SM Ram actually is in the system. Like you could just put SM Ram somewhere in DRAM. So we need to make sure that they don't try to just install their own handler somewhere off on the side. So that means controlling SM base, SM adder, SM mask, and anything in terms of SM control or even SM key. Because if they want to, when SM lock is 0, when SMM lock is 0, if you set a write to SM key, you've now reset the password. So potentially, if we had to lock it again, we couldn't unlock it. All right. So again, like I said, page real mode requires paging. So we had to create a shadow page table. Linear addresses in this case are actually just the segment and offset that's expected, and that's a guest linear address, which goes from we take that segment plus offset, we map it through our table, and that immediately comes out with a physical address. So we have to actually, when we're doing this and we're actually containerizing everything, the first thing we have to do is we intercept an SMI. When we intercept the SMI, we have to map SM Ram. We create entries for SM Ram inside of our page table. And after we've created entries inside of our page table, and we've configured all of the guests appropriately so that we can intercept this and run it and everything else, we then have our VMCB, which then kicks off and runs from there. But the other thing too is after we intercept, we also have to copy. We basically emulate what we emulate what happens during system management mode, such that we actually are copying the entire save state from the guest, putting it into our new VM, which is in SM Ram, and from there we just run it. We run the SMM VM. And when we run it until it gets the RSM instruction, in which case we then resume. The nice part about when we copy this and emulating this is that we can filter out known values before we return to the guest or when we're coming from the guest. So that means that if suddenly we notice that the instruction pointer changed wildly before this somehow, then we know that potentially the SMI handler could be doing something like trying to invoke code at ring 0 so that it can then modify OS data structures. Or possibly even copy out RAM. Like I said, I was trying to protect potentially a symmetric key living inside the hypervisor. So maybe you copy that, put it into one of the registers, put it into the save state area from your system mode interrupt handler, and then you want to put it back in your guest so that your attacker can actually get access to it and then pull executables off. All right. So I actually tried to do all of this. Apologize for some of the burbling. But let's see if I can get this going right now. All right. So